This video is on shifting equilibrium, or Le Chatelier's principle, and our note packet looks something like this. And depending on how lengthy this video gets, this may be a two-part video, and just we'll see what happens. I'm not sure. Okay, so what we've learned so far is that we can have a system at equilibrium. We also have learned just prior to this that we can have a system that is not at equilibrium, okay, and we talk about how it moves to reach equilibrium, and that was the whole discussion of the value of Q, the reaction quotient versus K. But this is a discussion of what happens if you have a system that's at equilibrium and it's disturbed somehow, okay? And so this discussion is something called Le Chatelier's principle. And obviously, Le Chatelier was a French chemist who studied disturbing equilibrium reactions, okay, or equilibrium systems. And so the underlying idea of this principle is that is what's written right here. If we have a system at equilibrium, okay, so all components are present and the system's at equilibrium, and it is somehow disturbed. And we're going to talk about three main ways we can disturb a system that's at equilibrium. And they are pretty much by a change in the concentration of a reactant or product, a change in the pressure if it's a gas reaction, or a change in the temperature, okay, at which the reaction is occurring. Then that reaction is going to shift its equilibrium position to counteract that stress. And in this discussion, you'll hear me, maybe not so much, but refer to these changes or these disruptions as stresses to the equilibrium system. And that's a big word. It's like a key word in textbooks and stuff. In terms of talking about a change that has happened to that equilibrium system and how that system reacts to relieve that stress. Okay, so it's all about, if you think about like a non-chemistry example, if you were stressed about, anything, you're going to try to do something to relieve that stress. You're not going to try to, most people aren't going to try to continue that behavior that's causing them to be stressed. Most people are going to say, I need to do something to reduce this stress, whether it's, working out or reading or hanging out with friends or whatever. You're going to do something that tries to counteract that stress. And that's the same thing with a chemistry example, just that we're talking about a reaction and how a reaction will react to reduce that stress. And I'm looking for my eraser, and of course I can't find it anywhere. Give me 1 second. All right, we'll use this. Okay, so the first one we're going to talk about is what happens when we change the reactant or the product concentration. So I'm just going to do a couple bullet points, and then we'll look at a specific example. Okay, so you might not understand it as I'm writing it, and that's okay. All right, and the second one. Okay, so again, this first, disruption or stress to our equilibrium system is a discussion in concentration. Okay, so changing how much reactant or product we have. So the first bullet point says that if you have a reactant or a product and you add more of it, so that would be increasing concentration. Okay, you raise the concentration of one of your reactants or one of your products. Then the reaction is going to shift, is kind of the word that's thrown around. The reaction is going to shift to use up that extra reactant or product, okay, regardless of which one it is. Because in that situation, the stress is that there's too much of it, so you have to use it up. The second situation can be, well, what if you decrease the concentration of one of your reactants or products? So that would be the second bullet point. If a reactant or product concentration is decreased, then the reaction is going to shift so that you make more of whichever thing decreased, okay? So this will make much more sense when we talk about a specific example, which will be right now, and that's what's underneath your, that little blank space. So of course it's the Haber process, all gas reaction. And so we have some bullet points. It says, how does equilibrium shift if H2 is added, N2 is added, NH3 is removed, and NH3 is added. So remember, this first section we're only talking about what happens if we change the concentration of my reactants or my products. Okay, so using what we just learned and thinking about that these things are causing stress to the reaction, we're going to go through these 4 bullet points. So there's my reaction up top, and I want to know, if I have this reaction, if it's at equilibrium, what happens if I add more H2 to the container? Okay, well, if I add more H2, obviously equilibrium is then disrupted, and I have too much of my reactant. I have too much H2. So in this case, remember my bullet point, it's going to shift to use up that extra H2. So the only way this reaction can use up the H2 is if the N2 and the H2 combine to make NH3, which would mean this reaction is going in the forward direction. If you think about it going the other way, the NH3 breaking down and making into an H2 would give you more H2, and goodness, that's not what you want. So if I have too much H2, the reaction, what is said is the reaction shifts to the right, okay? And what that really means is that more NH3 is produced. Now, most of the time, you'll see an answer being, shifts left or shifts right. But the real issue is that if we're talking about a reaction that's shifting to the right, what we're doing is we're using up the reactants and we're creating the products. Okay, so that's what that whole idea means in shifting right. If we were to shift left, which we'll see in just a minute, we would be using up my product and we would be creating my reactants. All right. So what happens if N2 is added? Well, it's the same thing. If I have too much N2, I'm going to shift to the right to use it up. So I'm going to shift right again in this case, and the reason is to use up that N2 to make more products. So I'm going to do the ditto marks. That means more NH3 is still produced. Okay, so the third one. What happens if NH3 is removed? So if I take some of this away from a system that's already at equilibrium, so this is that second bullet point where it's like I don't have enough anymore. So in this case, I don't want to use more up. I want to create more to offset this stress, which means, again, my reaction is going to shift to the right to produce more NH3. So it's also going to shift right. More NH3, same reason. It's kind of the same reason in all of these. But we're just talking about it from from a left-right discussion of what's really happening. And then what if the opposite happens in a completely separate example, that I add NH3 to my system that's already at equilibrium? Well, in this case, if I add NH3, I have too much of this. I need to use it up. The only way I'm going to use it up is if I turn and shift my reaction to the left. Okay, and in that case, we're going to use up the NH3, and we're going to create more into an H2. Now this is the answer, right? But this is kind of the why part. And at this point in our discussion, I think it's important that you know why, that is occurring. Okay, so that's an example of a reaction where, or talking about shifting equilibrium if you add or take away reactants and products. Okay, so the next one we're going to cover has to do with pressure. And there's actually 2 pressure examples we're going to talk about. One is the more common discussion of changing the pressure, and the other one is less common, but we have seen it up here on the AP test before, so definitely worth talking about. All right. So the first one is talking about changing the volume and then thus changing the pressure. Okay, so you have a bullet point that says if we have a volume decrease, we have a pressure increase, right? And that's because this is the big idea that P and V are inversely proportional, right? And that goes back to our gas chapter and all of that, discussion. So this is for gas reactions, okay? So for gas or gaseous reactions, should have been a comma, changing the volume of the container changes the pressure, which will shift equilibrium. Okay, and we'll talk about how in just a minute, but this is a really big takeaway, so to speak, okay, that if we have a gas reaction and we change the volume of the container, whether we decrease the volume and then increase the pressure, or whether we increase the volume and then decrease the pressure, right, either one, changing the volume of the container will change the pressure, which is one of the three things that's going to cause a shift in equilibrium for us for this discussion, okay? So here's kind of your bullet points. Let's see, how do I want to explain this? So we'll do the one that we said here. If volume decreases, then pressure increases, okay? Which means that the pressure is now too high. So to counteract this, the reaction will shift to the side with fewer moles of gas. And we'll do an example. I can do an example and then I'll do the second kind of bullet point. All right, so if the volume decreases and the pressure increases, it's inversely proportional. Pressure is now too high, right? We've increased the pressure. Pressure is now too high. To counteract that stress, the reaction is going to shift to the side with fewer moles of gas because we know fewer moles of gas will bring the pressure down. So here's my example, same one we worked with a minute ago. Okay, all gas reaction. Okay, so let's say we take the volume of this container, let's say it's in a balloon, and we decrease it. Right, so if I take that container and I decrease the volume, right, we know that the pressure is going to increase. That's a takeaway point that we learned a long time ago. So I've got too much pressure now. And so that means, in this case, my pressure is too high, and I need to think about which way is this reaction going to shift to alleviate that pressure that's too high. So here's where we look at moles, okay? And we look at moles on each side of the equation. So in my reactants, I have 4 moles total of gas. And on my products, I have 2 moles total of gas. All right, so in this case, if my pressure is too high, I need to decrease my pressure. So am I going to shift to make 4 moles or am I going to shift to make 2 moles? I'm going to shift to make the 2 moles because it's smaller and it will decrease the pressure. So in this case, my reaction will shift to the right. Okay, so that the pressure decreases to balance that out. Now, the opposite is true. I should have left some of that, but man, what a mess this was. So you can kind of squeeze this in. If you don't have room, I guess you don't have to write it, but I think it's important. So opposite is true. What if I increase the volume of my container? Then my pressure decreases. Pressure is now too low. So it's all the opposite, right? To counteract, reaction will shift to the side with more moles of gas. So again, right, if this is my reaction, and if I take my volume and increase it, then my pressure decreases, right? If my pressure decreases, it means it's too low. I need to make more pressure, right? And if I need to make more pressure, will I shift to the side with only 2 moles of gas, or will I shift to the side with 4 moles of gas? I'll shift to the side with 4 moles because it's going to make more pressure to counteract this. Remember, it's all about counteracting. So in this case, this would be a shift to the left. Okay? And that is the second idea in how equilibrium can be changed. So first we did concentration, and that was changing pressure by changing volume. So if you flip, there's a question. So if take a minute while I erase this and see if you can answer those. We'll go over them. And then I'll do the next heading, and then I believe I'm going to stop this video so that it'll be a part 1 and a part 2. Okay, so here we go. First one gave us this reaction in 204, giving us 2 in O2. How does equilibrium shift if first the pressure is increased by decreasing the volume of the container? Okay, so if I decrease the volume, the pressure increases. They just flat out told me that. If pressure increases, my pressure's too high, right? I want to lower it, which means I'm going to shift to the side with fewer moles of gas. So am I going to shift to the side with 1 mole, or will I shift to the side with 2 moles? I'll shift to the side with 1 mole. So we would say that this reaction will shift to the left. Okay, and that's to make fewer moles of gas so that I can lower the pressure. And then the opposite's going to be true if the volume increases. That means the pressure decreases. In this second example, P is too low, right? We want to raise it. And so the only way we're going to raise that pressure is if instead of shifting to the side with 1 mole, we shift to the side with 2 moles. And so we would shift, I can't spell today. We would shift to the right in this case. Second question is a good question. It says for the reaction of H2 plus I2 going to make 2HI, how does equilibrium shift when the pressure is increased by decreasing the reaction vessel? Okay, so pressure increases because we decrease the volume of the reaction vessel. Fine. So pressure's too high, right? I would like to lower the pressure to counteract that. But then if I look, I have 2 moles of reactant and 2 moles of product. And so in this case, because they're the same, you might guess, there's actually no shift. So that's kind of going to be an important takeaway point. If the moles are the same, the total moles of reactant and product gases are the same on both sides, you can change the volume all you want, and there will be no shift in equilibrium because those mole values are the same. Okay? All right. Let's do this last heading, and then that'll be the end of this video. This is kind of an involved section. All right, so the next one says effect of changing pressure by adding a gas that's not in the reaction. And this is the one that I said is kind of less common than the one we just talked about, but it has been on the test before, and we want to talk about it. So, if another gas who is not part of the reaction is added to a reaction at equilibrium, there can be a shift. And so this is where life gets a little bit weird. Okay, so if another gas who is not part of the reaction is added to the reaction at equilibrium, what happens is the mole fraction of the gases that are in the reaction decrease. Now let's talk about why. right? So the mole fraction of, say, gas A would be the moles of gas A over the total moles of gas. This would remain unchanged by adding that extra gas to the reaction. This would go up. If this value goes up and this remains unchanged, my mole fraction is then going to decrease. Okay, so if my mole fraction decreases, then the partial pressure of my gas also decreases. Okay, and so this is the big idea. So here we go. So for example, we're going to add helium gas to the Haber process. Okay. So by adding the helium gas to this reaction, it's not in the reaction, okay, but it's going to cause the mole fractions of each of N2 of H2 and NH3 to decrease. And because the mole fractions decrease, their partial pressures decrease, okay, and that's the takeaway. So because I have, again, back to this idea, because my pressure has decreased, I need to increase that. I need to create more gas to increase that pressure back up to where I want it. So this goes back to that same idea of, would I shift to the side with 4 moles or would I shift to the side with 2 moles, because now my pressure is too low, right? So remember, counteracting, pressure is too low, I need to increase my total pressure. So I'm going to shift to the side with 4 moles. So I'm going to shift to the left this time. Okay, so it's similar, but it's just slightly different because it has no discussion of talking about changing the volume. It's all about adding a different gas to the equation. And so I think that's it's important to talk about. And there are more discussions on how we can shift equilibrium, but that will be in part 2 of this video.